My name is Curtis Ritter, and I'm going to be doing my presentation on halo-angled implants. Halo is a short term for halo-angled implant. Halo refers to a method of how the implant tool is set at a particular angle as it fires atoms into the silicon. You're seeing a cross-sectional view in the lower right of a typical MOSFET gate at an intermediate stage in the manufacturing process. I will mostly present on the pocketed areas where there are three kinds of halo doping: P red, N orange, and N plus blue. I will present on why they are needed, how they are formed, and what effects they have, and then I'll conclude on the pros and cons. Two main reasons why we should use halo. The first one is getting dopings directly under the gate. That is labeled 1 red, as you can see from the lower right diagram. This helps eliminate punch-through. Also, the 2 labeled orange in the diagram is for the lightly doped drain, which helps barrier leakage and cell-to-cell leakage. The LDD also complements the first halo doping, 1 red, by improving reverse channel effects, but the shallow halo, shown as blue number 3, adjusts the voltage threshold and further reduces punch-through on the other side of the junction. The second reason is to help bring down the channel length and make it possible to scale further without affecting dibble, which I'll explain later. As the channel length gets shorter, there are other effects like VT roll-off that'll improve. However, this could worsen the short channel effects. We can't scale forever, and halo will only bring us so far. This will also have issues with R-out and leakage currents. Now I'm going to talk about how halo-angled implants are formed. First, boron is doped at an angle of up to 12 degrees at a dose of 2.2 times 10 to the 13 atoms per centimeter squared to create the P halo that you see in red. Next, arsenic is doped up to 30 degrees at 1.5 times 10 to the 13 atoms per centimeter squared to invert the P halo doping at the surface to LDD, N doping. Next, spacers are formed to protect the LDD area close to the channel. Now, phosphorus is doped on top of the LDD at an angle up to 30 degrees at 1 times 10 to the 15 atoms per centimeter squared. Notice how the lightly doped drain region is protected underneath the spacer. Now I'm going to talk about the channel area inside the box. You can see below the boxed colored channel an XY plot of the doping levels versus channel length. The greater the y-axis, the heavier the doping concentration at any particular point along the length of the channel. Two of the doping transitions have no inversion of doping, only different doping amounts of the same type. The only change of inversion happens on the edges where the vertical green lines indicate. Starting from the middle and moving our way outward, the light P substrate doping transitions to a heavier doped P+, that is, a non-inversion. Next, the P+ finally inverts to a lightly doped N, where we know of this being the PN junction of the MOSFET. Moving further outward, we transition from the N to a heavier doped N+. By making heavier doped regions at particular points on the channel length helps adjust the amount of needed barrier to control electrons to pass by, and to maintain the threshold voltage on the edges of the channel, improving VT roll-off. Let's look closely at the transition of doping gradients and their effects. It is important to see that the depletion region, the yellowish brown in the PN boxes, widths extend more in the lighter doped regions. First, P+ halo implants are used to create a gradual doping transition under the gate to improve device reliability and, of course, reduce punch-through. Halo LDD implants are used to maintain better channel length and prevent VT from getting smaller as the channel length modulation varies from the off to the on state. When the channel length for the lighter dope transition is too short, then VT drops with decreasing L and I-off becomes too low, and the depletion region extends too far, as you can see in the PN box of Figure 1. Figure 2 shows, with heavier doped regions, this happens more abrupt with higher I-off and with a similar but more abrupt drop in the VT, and the depletion region doesn't extend far enough. Figure 3 in the bottom right view PN box is what is being represented in the halo cross-section of Figure 4. Having the gradient on each side of the channel gives this needed gradual transition to lowering I-off while maintaining the short channel length. This also prevents the depletion region width from extending too far into the channel, limiting punch-through and allowing the depletion region to extend in the needed direction length away from the channel for improving things like dibble. Further away, the N+ limits the depletion region extension for more reduced VT roll-off, but with a non-inverted doping again. The next slide will show more details. Here you can see that the lightly doped pocket regions are doped with different doses, and improvements to the threshold voltage happens at shorter channel lengths for different doping. The red and wafer A line is an exception to being a non-pocket test, meaning no halo was used. The green line for wafer D is with halo, and you can notice how the voltage threshold has a peak and then drops off closer to shorter channel lengths. Further increasing the doping doses and energy for a pocket halo has more effects, as you can see, making the channel length become shorter with better specifications for the threshold voltage. Recall that dibble is drain-induced barrier lowering, and it occurs when the channel is so close that the electric field from the drain helps the gate attract carriers into the channel, effectively lowering the threshold voltage. The drain can lower the source channel barrier and reduce VT. You can think of this as being a change in the delta threshold voltage to the change in drain voltage. One way to look at dibble is with the added CD capacitor in the diagram of the gate. CD has electrostatic coupling between the channel and the drain. As the channel length is reduced, the CD capacitance will increase. Graded junctions adds more forward bias capacitance in series, bringing down the CD to further reduce these effects, but not for reducing junction capacitance in the opposite bias mode. From the IEEE source stated at the bottom, threshold voltage versus drain voltage is what is shown, as we know from dibble that more delta VT is less desired. Also, the triangles versus the squares comparison is 0.38 microns compared to 0.28 microns, and pocket halo versus non is compared. Dibble is seen to be reduced with halo, the green lines, in the form of delta VTH compared to the non-halo having more delta VTH, the red lines. So according to the IEEE data, halo helps with dibble. As seen here, a drawback is R out will get worse, because as we have transitions from doping regions, as our text shows, that the resistor mimics that transition. Another negative effect to halo implants is lower I-off. The figure right of the number 1 shows the heavily doped N+ drain circled. In deep saturation mode, this region acts like a scalar, further biasing the drain to the silicon substrate. There was a test ran by the source below in the block diagram where they created a VD reducing block and connected the MOSFET. They plotted ID versus VDS, and in the plot you could see there is 1 for non-halo and 2 for halo. The red is non-halo, and the green and the blue are halo. You can see the bend and the ID roll-off is different. In conclusion, there are pros and cons of using halo-angled implants. The pros: for P+, it prevents punch-through and allows for better reliability. The LDD helps reduce dibble and holds VT roll-off closer to the edge of the channel. All 3 implants together allow for smaller scaling and shorter channel length under the gate while maintaining dibble and VT roll-off. The cons: the P doping alone may hinder channel length modulation. Reverse coupling capacitance will increase along with short channel effects, which results in higher R out, lower I off, and increased leakage current. Halo implants can only provide limited scaling. In summary, though, the pros outweigh the cons. It provides us one extra tool in bringing us one step closer to a smaller node size.